Okay, now I'm not gonna spend too much more time on this because we did all this last time, but I knew it needed to be reinforced. It's one of the things that give people most trouble in a pre-calculus course. Okay, so we got an algorithm for constructing graphs. Okay. And as I said, you ought to get big old solid gold plate and etch this on that plate, just to keep your attention, okay? Here's your method. Now there's some kind of asterisk. I can't use an asterisk since I use that for multiplication. But you know, this is a little note. Y equals 0 gives you your x-intercept. And your x-intercepts, because often there's more than one. And this is usually when the numerator equals 0. Okay. So it's easy to find the x-intercepts for all of these. X-intercept here is going to be 4. X-intercept here is going to be 4. Okay. And y equals 0, x is going to be 4. If x is 4, that's going to make y 0. If x is 4, that's going to make y 0, right? Here, your zeros are going to be -3 because if x is -3, this is 0, which means the whole thing is 0. If x is 5, this is -5, this is 0 again. And if x is -1, so you know what your x-intercepts are. You just read them off if these things are factored. Now, you know, if the factors, you know, if you got like a 2x plus 3 here, well, you're going to have to solve a simple equation. That's easy. So my point is then, usually you get your x-intercept when the numerator is 0. There's an exception to that because if the denominator is also 0, you don't get 0. You get an undefined point. Okay, you call that a removable singularity. Now you're going to have to worry about that in pre-calculus class. I'm not going to do removable singularities except just to mention it. You want to get the most basic method down. So we're not going to worry too much about this in this course, but in pre-calculus, we're going to have to worry about it. If you get this method down, then it becomes pretty easy to understand the exceptions. Okay, x equals 0 gives you the y-intercept, usually. For the same reason, if you got a 0 of the numerator that matches a 0 of the denominator, then you might not have a y-intercept. The thing might not be defined when x equals 0. Not going to worry about that. I'm not going to give you an example that does that. Okay. Then you want to find the asymptotes, which occur usually when the denominator is 0. There are exceptions that we're not going to worry about, but I'll tell you what the exceptions are. Again, if the 0 of the numerator and the 0 of the denominator match, then you might not have an asymptote. You might have an undefined point. There's a little more to it than that. Again, we're not going to worry about it. So let's see how this works out. Let's take the first one. You got it. Now, I keep urging people, but I don't see anybody doing it, to write out what you're doing at each step. Partially because, you know, we don't have a whole lot of students in here, so I don't have to spend a whole lot of time grading. So I'll go ahead and decipher your problems, no matter how you write them out. Do my best. Okay. If you got something there that I didn't see and you find that in the grading, okay, I'll fix it. Fair enough. At a big class, I wouldn't be able to do that. I'd have to say, you're going to have to give me some kind of structured solution. I don't expect miracles at this level. Nobody, I don't think, will. But if you got a class of 30 people and somebody's teaching 5 sections, as would happen at a lot of universities and so forth, they're not going to take something sprawled all over the paper. Okay. First place graduate students are probably, actually, it's probably been graded by a computer, which is awful. But that's the way it is. Okay, well, anyhow. And then also, probably going to be graded on the answer rather than the process, which I think is even worse. There's a contrary argument, just my opinion. Okay, y equals x minus 4 over x plus 6. My whole reason for that digression was to say, write out what you're doing at each step, write a few words, like a heading, like arrange this thing into paragraphs, arrange it into steps. Okay, so the first step is, let's find the x-intercept. And put down y equals 0. Every time you do this, it reinforces the fact that you want to do that, and you're not going to forget it when you need it. If you do a bunch of problems, actually write it out like this. You don't write it out. You know, I'm trying to learn general relativity. It's kind of a lifelong ambition. Haven't really had time to get into it. I'm probably too old to learn it very well. Okay. And I'm trying to do it without writing stuff out. Now, if I really wanted to learn it, if I really needed to learn it, I'd be writing stuff out. But I'm trying to do it without writing stuff out because I'll end up with maybe a deeper understanding. And whether I end up with a deeper understanding or not, it challenges my brain a lot more. I mean, it's going to challenge my brain plenty anyway. If one person in 1,000 can really understand it, and I'm probably not quite at that level. Okay. Yeah, maybe one person in 897. I think that's kind of my latest estimate. Yeah, probably not that good either. Okay. You don't want to make the challenge any harder than it needs to be. I'm making it harder than it needs to be just to keep my brain exercised. Okay. I'm doing it without writing stuff out. You need to write stuff out. Almost everybody needs to write stuff out, and I can't emphasize it enough. Write out what you're doing. Okay. Okay, so x-intercepts occur when y equals 0. If y equals 0, that means 0 equals x minus 4 over x plus 6. How do you solve this equation? Well, you can solve it looking at it. If x equals 4, you know this is going to be 0. Okay. And if that's best you can do, okay, but let's make sure we understand why. We multiply both sides of this equation by x plus 6. We get this. And of course, I write x plus 6 over 1 because I think everybody needs to do that to understand what's going on with the fraction. Otherwise, you're crossing stuff out and canceling whether it's appropriate or not. Some people will cross out the 6 and the 6 and leave the x there. Okay. That would not be unusual given the preparation of students come into our courses. Okay. It's rare that we find a student who really knows the rules for cancellation. Okay. So I don't like to cancel. But if you multiply x plus 6 by 0, you're going to get 0. And you know that I could, okay, when you multiply fractions, you multiply the numerators and you multiply the denominators. Makes no difference whether it's x plus 6 is here and the 1 is here, or if the x plus 6 is here and the 1 is here. It's going to come out the same. So you know that you have x plus 6 over x plus 6, and that's 1. I would write out the details of that. I don't necessarily expect you to write out the details every time, but since we can write it this way, because if I multiply the numerators, I get the same thing I did up here. If I multiply the denominators, I get the same thing. So it's got to be exactly the same. So that then I add 4 to both sides. and I get x equals 4. Of course, I already knew that that was going to be a solution because x is 4. Okay, so I don't necessarily expect you to write out all these steps, but when you see this equation, those would be the steps to solve it. Again, it turns out that we can kind of shorten this, just say, okay, as usual, the numerator equals 0. A shorter solution. Numerator 0, so x minus 4 equals 0. So x equals 4. Now, that tells us something about the graph. Tells us when x is 4, y is 0. So here's our graph. Here's the point. Four zero. Okay. Next one, we find the y-intercept. That's when x equals 0. Well, that's always, almost always very easy, unless you got a really weird function, and you're not going to have a really weird function. So you get y equals 0 minus 4 over 0 plus 6, which is minus 4 over 6, which is minus 2/3. So now we know. Yeah, where's minus 2/3? Well, if this is -1 here, well, here's -1/3 and here's -2/3, right? You just divide this interval from 0 to -1 into 3 parts and take 2 of them. And that puts your y-intercept here. So that's the point. 0, -2/3. So we've got 2 points in the graph, and that's all we can do about the intercepts. Now, when we go to this problem, well, we're going to have 3 x-intercepts. But if x is 0, it's easy to calculate y. And we're going to have the y-intercept here. Same thing down here. So it takes care of the y-intercept. Again, write down the heading here. Put a big underline on it. You don't have to use gold, at least not real gold, highlight it, okay? Be expensive, but make sure you write down what you're doing. So you can look back and say, yeah, okay, I found the x-intercept, I found the y-intercept. You don't have to remember that those calculations you did over there give you the x-intercept. You know by the heading where to look if you want to check your x-intercept. You know where to look if you want to check your y-intercept. Write it out. That might not work for everybody, but I can't think of a student I've ever had that it wouldn't work for. Okay. And maybe I just didn't recognize it. So I'm sure there are exceptions. Okay, what's the next thing? Find the asymptotes. And it has to be in parentheses, because sometimes you only got one asymptote. Okay, well, asymptotes occur when the denominator equals 0, unless there's an exception. And there isn't one here, so we're not going to worry about it. Asymptotes right out, denominator equals 0. Denominator is x plus 6. So x equals -6. Now, what do you do with an asymptote? This is a vertical asymptote. You draw a picture of the vertical line x equals 6. Now, I haven't left myself quite enough room to do the long run. I can kind of do it, but maybe that's some total over here. Now, how do you do long run? You can consider what happens as x approaches infinity or x approaches negative infinity. And let's go ahead and write that out. As a reminder. Okay. Well, if x is a really huge, if x is a million, then what's x minus 4 over x plus 4 close to? Well, a million minus 4 is practically a million, isn't it? And a million plus 6 is real close to a million. Okay. If I show you a million things, you wouldn't be able to distinguish if I also showed you 999,996 things. It would look the same. You wouldn't be able to distinguish it at all. Okay. And if I showed you 1,000,006 things, 3 piles of 1,000,006 things, one with 1,000,006, one with 1,000,000, one with 999,996, they look exactly the same to you. So these numbers are almost exactly the same when x gets big. Which means that if you divide one by the other, it's almost exactly 1. Okay. There's your reasoning. Now, if you need more work on that reasoning, you can check the videos and open math and see how they do it. You can also do a long division, but it's kind of unnecessary. We did that last time. So if you want to see that, look at what we did, because at least one person did a long division, not a bad thing to do, but really not necessary in this case. So the long run is as x goes to infinity or negative infinity, y goes to 1. Well, that means we better write a line, or we'll put a line here for y equals 1. Okay. Now, what's an asymptote do? A vertical asymptote? It acts either like the reciprocal function at the y-axis or the reciprocal square function at the y-axis, and maybe reflected across the x-axis. So if you had a reciprocal function and this was your y-axis, what would it look like? Well, it could look like this maybe. Okay, and if it does, then that means you would have to come down here and approach this asymptote. Or it could be upside down and it could look like this. Okay. Now, which is it? Well, which is it? It's got to be this, because if it does this, actually conceivably it could. Okay, it could come down here and go through this point and come back up through this point. Okay, so maybe it could do this, except it can't. Got to be asymptotic to this line and this line. It can't go through 0 here. So it can't come down and go through this. If there was a zero over here, though, it probably would. Okay. Okay, so it doesn't do this. You're left with this, which explains it just real well. So we're gonna say, well, okay, this is gonna work. One way or another. It could do something like this. Don't know for sure it has this shape. And you could determine a lot more about the shapes once you learn a little bit of calculus. Well, we're not going to touch that here. You have to learn not a whole lot of calculus halfway through the first semester. The calculus course, you would know how to figure out whether a thing waves like this and whether there's an inflection point and all that stuff. Okay. Don't worry about it here. On this side, it does this. It approaches this asymptote over here. And there's your graph. So what you need to know, at least one of you, you know, most of you, are getting the zeros. Emphasis on where we get that asymptote. All right. Well, we're using up more time than we really have to spend on this. This is some other stuff we need to do. So let's quickly dispose of this one. For this rounding book, but I'll just kind of show you. And I'm not going to write it out in detail. The numerator 0 when x is -3, 5, or 1. So here's 5. Here's -3. And here's 1. If you go through the entire process, as I've outlined it, write your headings, do everything. Well, that's going to be an easy one. And find the y-intercept. That's also easy. Okay, well, my function, let's write it out. There it is. Okay. Now your asymptote happens when the denominator is 0. Denominator is 0 when x equals 2. So you have a vertical asymptote at x equals 2. Long run. I did this last time, so review. Look at the video if necessary. But you have, if you multiply these three terms out using the distributive law. Don't bypass the distributive law. You can't multiply these unless you use the distributive law. It's x cubed plus something over x minus 2. As I indicated last time, I'm not even going to write out the x minus 2. All I care about is the leading term, the highest power term. If I divide x cubed by x, I get x squared. It acts like x squared for large x. What does x squared look like? It looks like this. Meaning that as x goes to infinity, it's got to do this. Got to go up on this end. Got to go up on this end. Now I haven't yet found the y-intercept. And that means that there's something wrong with what I did here. And I don't see what it is. There's a y-intercept. Oh, never mind, yeah. I just looked at the numerator. Forget what I did. The y-intercept, let x equals 0. You get 3 times -1 times 5, which is 15, divided by -2, which is -7/2. So now what happens? Well, if it was just an x squared function, it would have to come down through here, through some point like this, come down here and then up here, okay? Maybe something like this. But it's got these zeros here, so it can't do this. It's got an asymptote here, and that's even more important. So we have to come down from positive numbers. Positive y. Got to come down through here. And we got to then get through here. We've got to turn around sharply and come back up through here and then approach this the same way the 1 over x or 1 over x squared would approach its y-axis. And of course, we have to understand the reciprocal and reciprocal square functions. They have a good idea of why the asymptote occurs. So everything we do is based on those functions. So make sure you're very conversant with those functions. Down here, well, we'd either have to come down from this asymptote through this point and then get back up, but there's no place to get back up because there are no other x-intercepts. Okay, if x is any number but -3, 1, or 5, you're not going to get 0 here. Got to make sure you understand that. Okay, so what's going to happen is we're going to come up through here, and then we're going to go on to infinity, and that's what that looks like. Okay. The last function is y equals x minus 4 over x squared plus 5x plus 6. Well, we got a factor. Factor the denominator, you're going to get x plus 2 times x plus 3. Now, remember, it would be possible you get an x minus 4 when you factor the denominator, not for this function, but there could be another function. Okay, like x squared plus 5x plus 1. That would give you an x plus 4 factor in the denominator, which would divide the x plus 4 in the numerator. We would call that a removable singularity. That's worth hearing. I have more time, I'll write it down, but that's something you're going to see in your pre-calculus course. Let's just get the bare bones of this process. Okay, so in this form, and I'm not writing it out, although you need to write it out. It's x minus 4 is going to be 0 when x equals 4. So we got the point 4, 0. Denominator 0 when x equals -2 or -3. So x equals 3 here, we got x equals -2 here. Long run, I will write out it's like an x over an x squared. So it acts like x over x squared, which is 1 over x for large x. What's that look like? It looks like this. And of course, you got to know that instantly because you got to know the basic toolkit functions. There are other ways to reason it out, but that's the easiest way. And you got to know those functions for all the other stuff. So make sure you really know what those functions look like. Okay, well, now this function has an asymptote at y equals 0, but that's not large x. So this function is not going to have an asymptote at y equals 0. So what we really have, though, is this part of the function. And we discard everything that doesn't happen for large x, because it's only for large x. For small x, it has to do the stuff that it has to do here. So for large x, we know that this function is going to start over here with an asymptote at the negative x-axis. It's going to start here. Over here, it's going to end up close to the negative x-axis. Now it's going to have a vertical asymptote at x equals -3. That's about it. It's got to have an asymptote to this line and an asymptote to this line. So it's either going to be upside down, like this, or right side up like this. It's not going to touch the x-axis because there's no 0. We don't know how high it's going to be or how low it's going to be. And there's a detail that I'm not going to take time to mention. I'll mention it, but I'm not going to talk about it. Okay, let's do this. Reason is this asymptote comes from the factor x plus 3 in the denominator. So near this point, it's going to act like the reciprocal x plus 3 function, 1 over x plus 3, which is 1 over x shifted 3 units to the left. So we have like a 1 over x graph shifted 3 units to the left. It's got to do this and this. Of course, at x equals -2, it's going to have to do this. So it's got to turn around real quick before it really acts totally like an x minus 3, 1 over x plus 3 function. It's going to do that. Now that's an explanation, but this is just the way it's going to work. And your pre-calculus course, you probably learned that, well, let's just substitute a number between -3 and -2 and see if this is positive or negative. Turns out it's positive, so it's going to do this. All right. There's more to it, but again, you will learn. The y-intercept, which we never did, is going to be -4 over 6. Coincidentally, that's -2/3, same one we had before. So this is -2/3. I guess I'm doing this graph in blue, so let's go ahead. If this blue means we're going to come up and down here. We're going to go through here. We might come up a little bit, and then we're just going to level off at the x-axis. Kind of similar to the way the first one behaved. I don't have that handy, so I won't show you again. There it is. That's the process. It's a pretty quick process. If your arithmetic, your algebra doesn't get too complicated. All right. That's the overview. Okay. All that didn't leave us a whole lot of time to do rational equations. There's one fundamental principle you got to know. It's that if you have an equation with denominators, you multiply both sides by the common denominator. You automatically do that. Now, there's another thing you do, I'll mention as we go through it, which is you have to say, well, this only works if the denominator isn't zero. See how it works out. Okay, so we multiply the common denominator. You want to work this out. Okay. You want to get better at writing out a short phrase or something that describes what you're doing, because that way you're going to remember to do it. You're going to get better at remembering to do it. You don't remember to do it, and you have this equation, you're dead in the water. You cannot solve it. Okay, so the common denominator. And let's write out what the common denominator is. What's this? So we have this. And I know I'm going to run out of room down here, so I'm going to continue on down here. And just write out everything. Be careful to multiply this by 0 as well. If I had the 12 over there, you'd have to multiply it by 12. Since I'm multiplying it by 0, I don't ever have to multiply all these three things out, which is why I chose to use 0, because we don't have a lot of time. But we could. Have to use a distributive law. We could multiply those out, and it wouldn't overly complicate our solution if we did. Okay, so now what do we have here? Well, we see that the x plus 6 could be moved over here to match this x plus 6. So it goes away. So this first term gives us x minus 3. Well, kind of stuck there. Let's make a better for you. Okay. And then over here, well, the x minus 3 and x plus 2 occur here. So we could swap this with the 1 and divide that, and it goes away. And we end up with x plus 6 times x squared plus 5. And that equals 0. Well, it's not too bad. Let's multiply this out. Well, I'm going to multiply them out like this. I'm going to say, okay, we got x minus 3 And then I'm gonna multiply these two together. And that's gonna give me x squared minus 2x minus 8. Don't tell me that that equals x squared minus 8. It's not this times this plus this times this. It's x times x minus 4 plus 2 times x minus 4. You write out the distributive law in detail. If you don't do that and get used to doing that and understand that, you're going to be tripping over the rest of the course. Okay, let's try not to do that. Over here, I'm going to write this out explicitly using the distributive law. And you should, incidentally, you should do the step of writing out x times quantity x minus 4 plus 2 times the quantity x minus 4 here, and working out this x squared minus 2x minus 8. Because I still see a lot of people not doing that. And you don't get that minus 2x unless you do. Okay, anyhow, okay, over here. X plus 6 times x squared plus 5 is x times x squared plus 5 plus 6 times x squared plus 5. Now, I'm going to write out the distributive law explicitly here. We're going to get x times x squared minus 2x minus 8 minus 3 times x squared minus 2x minus 8 plus x times x squared plus 5 is x cubed plus 5x. 6 times x squared plus 5 is 6x squared plus 30, and that gives us 0. Well, we're gonna need a little more room, so let's take this, bring it up, and multiply it out. X times x squared is x cubed. X times negative 2x is minus 2x squared. X times negative 8 is minus 8x. Then we get minus 3x squared plus 6x plus 24. And I'm already out of room here. And then we're going to have plus x cubed plus 5x plus 6x squared plus 30 equals 0. Okay, I've got an x cubed term here, and I've got an x cubed term here. So I'm going to have 2x cubed. I've got an x squared term here, an x squared term here, and an x squared term here. Minus 2 of them, minus 3 of them is minus 5 of them, plus 6 is 1. I'll color code these. Okay, minus 2x squared, minus 3x squared, plus 6x squared. So I think I've got all my x squareds. Then I've got minus 8x and plus 6x and plus 5x. And that gives me how many? Negative 2, negative 8 and 6 is negative 2 and 5 is 3. Then we've got $24 here and 30 here, so we've got plus 54, and that equals 0. Now, there's nothing we can factor out. We've got a 2 here, we've got a 3 here, so there's no number that divides all of these. And this doesn't have an x, so there's nothing with the x in it. At this stage, we're just stuck trying to find the blame zeros. And the rational roots theorem, if you talk about that, which I don't much, tells us that we're gonna have to divide by something involving the factors of 2 and something involving the factors of 54. And try all possible rational numbers. And you know what? I made this up randomly. Maybe 1 chance in 50 that that's going to factor over rationals. Okay, maybe it's higher than that. I haven't worked it out. In the real world, it doesn't happen. I don't emphasize it because it's useless. Okay, now for problem solving aspect, fine. I think there are more important things to problem solve. So I mention it, I touch on it, and I don't test it except as an extra credit problem. Okay. Stop. Okay. I spent at least 24 hours, maybe 30, instructing and stuff, okay? About 2 hours making up the problems. And the rest of the hours getting the solutions correct. By correct, I mean they had to randomize because everything randomized. This is one version. I emailed 20 versions. So you have all the practice you need. If you do everything on this, then you're almost guaranteed to do at least okay on the major quiz. There's stuff in the major quiz that isn't on here, so you don't just ignore everything else. But I recommend you start by working through all these problems. Okay? How big is your work? Okay, I'll get a break next week. If you're working next week and send me copies. I'd take a couple of days before I get back to you, depending what kind of projects I'm into otherwise, but I will get back to you with feedback. Okay, or partial. You can select the problem you send me. Matter of fact, if you're absolutely sure you know how to do a problem, I just assume you wouldn't send it. You're going to have many pages, they say. I can sort through the pages pretty quickly. Now, if you do this, organize your work. It's good for you to organize your work. It's a good learning. Okay. I'll sort through it if it's not organized, but you know, if you got a problem sprawled out in several pages where you're working on a different problem on some of those pages, I'm not going to take the time. I just can't justify taking the time. Get it reasonably organized. Do the things I tell you to do. Write down what you're doing. Here's what I'm doing. I'm finding the zeros of this thing. Okay, here's how I did it. Well, okay, now I'm finding the asymptotes. Here's how I did it. Okay, now you're not going to have to worry about asymptotes on this midterm. Okay, that comes up. That's coming up right now. Okay, I'm graphing this quadratic axis of symmetry. Dot, dot, dot. Okay, zeros. Dot, dot, dot. Maybe there aren't any, maybe there's just one, maybe there's some quadratic function. Those are the options. Okay. Transformation. Okay, here's my vertical shift, here's my vertical stretch, etc. Okay. You write that out and you reinforce that that's what you do so you don't forget to do it when you get to the test. And if you leave something out, I can say, hey, go back and look. You have a detailed solution. They're in words. You got to read words. Okay. And you can do that. Yeah, I've seen everybody reading words at one point or another. I know you avoid it whenever possible, but read words. Okay. And I know you don't avoid it. You wouldn't be at the level of this course if you did. Okay. I recommend that you write it all out. There are 34 problems here. Some of them are trivially easy. I still wouldn't skip anything unless you're very sure you totally understand. Some of them are steps in understanding something that's going to be on the test, and I'm not going to test you necessarily on the steps. I'm going to test you what the steps are leading to. Okay? It goes back to know what the steps are leading to. So I recommend that you work this, even if you have to read the solution of what to do step by step and write it out. Now, if you had to rely heavily on the solutions, that means you didn't really learn it, but you learned something about it. Then go to one of those random things and work them without looking at the solutions, see how you did. Okay. And then you can simply work on that if you have, here's what I missed out. I can't get this straight. What am I supposed to do? Okay. Beating your head against the wall is not something I recommend, although it's tempting. Okay, it's bad on the wall. Depending how thick your skull is, it's probably bad in your head too. Get to where you can work all these 34 problems. And you'll have a pretty good foundation. You're not going to ace anything just by doing those 34 problems. If you've been doing the homework, it'll probably pull a lot of stuff into perspective, or you might even ace everything, but start with being able to do those problems. Then go back and review. Review the problems. You're going to have to spend a good bit of time preparing for this midterm, depending on how well you've done in the course so far. Okay. Whatever time you can spend, of course, it's critical. You want to pass it, you want to pass it with a decent grade if possible. Okay. It's a gateway to further math courses. It's required for your curriculum. Maybe a D is good enough. But I certainly hope nobody makes less than a C in this course. Because if you make a D, you haven't learned, you've learned stuff. You're not really prepared to take further math courses that are based on this. Okay. And of course, the D is bad on your transcript, but based on graduation, do this or graduate, or do you get to graduate. Okay. Now, nobody in here needs to settle for D because everybody's got the ability to do better than that. You have the time, and you're going to put in the time, and you're going to do it the way it needs to be done. That's a question. Fair enough? I don't know if it's fair enough, but that's what it is. Okay. I think it's fair. I think my administration would support me in thinking that's fair. Who knows what the state system will do? I don't know what they're thinking these days. And I don't care. Okay, I'll teach the course the way it needs to be taught, whether they tell me differently or not. Now, I'm doing what's supposed to be done. Okay. And they don't really try to dictate how it's done. All right, well, there we have it. And the whole national, everything goes on that leads to the design of these courses. It comes from the national curriculum, which is a stupid mess. Now, if I designed the national curriculum, it'd be a stupider, messier mess. So I'm not necessarily throwing stones at people. I'm just saying there's some real flaws in the curriculum, and nobody can agree on what they are. So we're stuck with what we got. Okay. Enough raving. Let's do some mathematics.
How long?
Okay, the question we have is, what are the deadlines? Okay, now that's, people have been talking about this before class started, and they said, no, we're not going to do that. We're going to talk about this after the class starts because I'll forget to say something and see what happens. Well, that's okay. I'm glad you asked. And it's absolutely necessary. You're going to get an email. Okay. You want to do the major quiz. There's a major quiz and a midterm. You want to do the major quiz at least a few days before you do the midterm. The deadline, I've moved deadlines way back. Okay, deadline is going to be 2 weeks from last Tuesday, 12 days from now, the day that our next class meets. Okay. For the major quiz. The final will be the end of that week. And I guess I would accept it, I think I said Friday, but even Saturday. Okay, it's not done online, it's done in the testing center. You don't get to use your calculator. You don't get to use Desmos. You don't get to use anything but a simple calculator that does arithmetic for you. It won't graph, doesn't have memory. You can't access the internet with it. It does the arithmetic. Okay, and you will need to do some arithmetic. The calculator is going to be handy for that. It's a Casio 260FX or FX260. I forget which was first. Just a bare bones calculator. I don't know what they cost after inflation, but they were under $10 last time I looked. And they're pretty much level what you get in Cracker Jack boxes. Okay, they do what they do. They do it well. And they don't do anything extraneous. If they're graphs, you have to instruct them by the methods we're learning. There are the methods we've learned. We construct graphs based on basic functions using transformations. You know how to do that. And you will if you do work through this. There's a whole lot of how to use transformations. Excuse me. Okay, what else? I don't put a time limit on the test. Major quiz, I think it has 10 problems. I've done 3 major quizzes for 3 completely different courses. This, multivariable calculus, and the University of the calculus-based physics course, and they have different numbers. But I'm thinking it's 10. I don't get to less than this every time. Certainly not less than 8. And I don't think it's more than 10. I don't think. Anyhow, there's no time limit. So go in there, be sure you've been well fed. Okay. Don't overhydrate. Because some people, when a test is designed to take an hour and a half, actually isn't reasonable to do in an hour. Some people take all day. You shouldn't have to do that. But if you can work it out in a day-long session, I want you to understand what you're doing. It means that you've both done it and you've learned something by doing it. And maybe you've learned something about how to prepare so you can do it faster. Okay, I'm not testing speed. Okay. See if there are any other questions. Let me pause. Okay. The Zoom record button is an invention. Okay. So, photograph this function. Now, as I've advocated repeatedly and repeatedly and repeatedly, we want to write down at each step what we're doing. Okay. And you all started to get pretty good at that. So just be sure you really get the system. I will say that the midterm is late enough that I might put some optional problems on it, on polynomials and rational functions. Okay. So if you nailed this down and you really kind of want to, and we're going to move into exponential functions when I come back, and inverses of rational functions, which isn't assigned yet. So if I do, those problems would be optional, meaning go ahead and do them if you have time. And you think you can do them. If they improve your grade, I'll count them. If not, I'll just throw them out on each problem. There's probably polynomials if you do that one, and it raises your grade. I average it in. Okay. And if you can't do that, we could do the one in rational function and raise your grade. Put it in. Okay. So just another incentive to nail this stuff down. It could help. Won't be on the major quiz, but it'll be on, it might be on the final. And if you want it to be, remind me to put it on there. Probably never. But there you go. Okay, so first of all, this is an abbreviated. Yes. And you want to look back at what we did in the MDE course, because everybody can profit from that. It's a process. When I wrote down the algebra. Okay. X-intercept 1 for 0, y-intercept occurs when x equals 0. Asymptotes. Where the denominator might be 0, you can have long run behavior. And there's more and more detail, but I'm kind of condensing this because we don't want to spend all day on this. Kind of spent all day on it last hour. Refer back, use that for more detail. Okay, but the x-intercepts. I'll expand this a little bit. We go, okay, here, x-intercept. Like 0. Write that down for an underline. It takes about 5 seconds, depending on how fast you write. And you can go back to the video and time and do that. See. Okay, I don't know how many took. That's my guess. Okay, so they got to get 0 equals x squared plus 4x plus 3 times x minus 5 over x plus 2. How do we solve this? We multiply both sides by the denominator. That's how we always solve an equation that has denominators. You don't want denominators. You don't want to be dealing with fractions. You don't want to be dealing with denominators. You don't have to. Save yourself time by learning to do this because nobody seems to be doing it reliably. Okay. So we're going to multiply x plus 2 by 0. And when I write down the x plus 2 here, I'll do an x plus 2 over 1. Remind myself I'm multiplying by a fraction, and remind myself of the rules for multiplying by fractions. Now I know that multiply fractions by denominator is going to be 1 times x plus 2. So I could write it as x plus 2 times 1. With the x plus 2 here and the 1 here, it'd be the same. And the x plus 2 divides the x plus 2, gives us 1. And we don't cancel. I see people try to cancel this 2 with this 4. Okay. And then cancel this 2 with this 2 and leave this x. I see people do bizarre things because they don't understand the rules for cancellation. You understand the rules for cancellation by saying that this can be rearranged so you have a 1 here. Now there's also a rule you cancel factors, and this is a factor, and this is a factor. So that's okay if you understand what factors are, but everybody's having trouble with factorization. Okay. So not sure what we're supposed to do here, but okay, so we get this. Now, how do we solve this? Well, either this is 0 or this is 0. Well, we immediately know that this is 0 if x equals 5. How do we get this equals 0? Well, we can set it equal to 0. We can write x squared plus 4x plus 3 equals 0 and solve that equation, right? So this devolves into the 2 equations. It's important to write this word or, right? We don't write. It'll seep into your brain. If you don't write it, it's unlikely to seep into your brain. And I just know that from experience. People that write these things out eventually get it. And people who don't, generally don't. And a lot of times they get quite a bit of it, get some partial credit, but don't involve they could. Okay. Write it down, write it out. So solve this equation. You can use the quadratic formula if you want to. That's fine, but this is really easy to factor. And you really need to be able to factor trinomial. If you didn't factor it, and some people did, some people didn't. Okay. It's just one step, right? A factor. Then we know if this occurs, x plus 3 equals 0, or x plus 1 equals 0, right? So now we know. So our solution is x equals -3, or x equals -1, or x equals 5. You can check that. If x is -3, we get 9 minus 12 plus 3 here. Well, 9 and 3 is 12, minus 12 is 0, so that makes this 0, so the whole same thing is 0. If x equals -1, we get 1 minus 4 plus 3, which isn't 0, which is 0. 1 minus 4, 1 and 3 is 4, minus 4 is 0. Okay, and if x equals 5, x minus 5 is 0. All those wipe the whole thing out and make it 0, so we check. Okay, well, all of a sudden we've got information, we've got our x-intercepts. Let's start constructing a graph. X-intercepts are -3, 0. -1, 0. Oh boy. Thought I could write that fast, but I just didn't get away with it. Five zeros. That's a lot of information. You got to go through the x-axis at every one of those points and at no other point, because no other value of x makes the numerator 0. And this sure ain't going to be 0 if the numerator ain't 0. Okay. Now, sometimes the denominator would also be 0 and the numerator 0, and we have to deal with that. Probably not gonna, probably gonna leave it open math to clarify that, because we're still having trouble with the basic. Okay, so that's our x-intercept. Okay, well, let's go up to y-intercept. X equals 0. That's our heading with what we're going to do here. And this is quick. So x equals 0. So y equals 0 squared plus 4 times 0 plus 3 times 0 minus 5 over 0 plus 2. That's going to give us 3 times -5 over 2, -15 halves, which is -7.5. So I'm going to say, okay, let's just put that here. 0 -15 halves. Okay. asymptotes. Denominator equals 0. X plus 2 is the denominator. It's equal to 0. X equals -2. That's a vertical asymptote because X equals -2. The statement X equals -2 has a graph that looks like this. Now it should be halfway between -3 and -1, and I missed it, but you get the idea. Okay. And then long run. Well, in the long run. I'm gonna write this pretty small to keep it on the same board. Long run. Y ultimately is x cubed plus a bunch of stuff over x plus a bunch of stuff. Why x cubed? Well, if I multiply this x by this x squared, which this says to do, I get an x cubed and I don't get any higher power of x. And we use the highest power of x here and the highest power of x in the denominator. Now, can you see what I've written? Because it's pretty small. If your eyes are good. A few years ago, Miles could have seen it from the back of the room. I'm slowly approaching middle age, and it's changing, but okay. And if you don't see that here, look back. Stuff I wrote out bigger, or look at the video because it should show kind of the video. Okay. If I divide the highest power term of the numerator by the highest power term of the denominator, I get x squared. Which means that in the long run, this is going to behave like the x squared graph. What does the x squared graph do? It goes up here, and it goes up here. It goes up on both sides. So circle that and indicate that the graph is going to go up here. Got to be up here. Okay. Well, now I know that the graph is going to come down from high values here, essentially just the x squared values. If you put in x equals 100 into this, okay, 100 squared over 100, sorry, 100 cubed over 100 is going to be 1,000,000. I'm sorry, x cubed is going to be 1,000,000. X is 100. It's going to be 10,000. Okay. If you actually evaluate this for x equals 100, it's going to maybe miss 10,000 by 1 or 2%. It's not going to miss it by much. In other words, when x is 100, this graph, the y value is pretty close to 100 squared or 100 cubed over 100. Okay. Pretty close to this. And same thing for big negative values. So you know they get really big. So the graph comes down from here. Maybe it kind of levels off a little bit, but then it goes down. Here. Asymptotic for this. Eventually, it looks a lot like the reciprocal function. Because you got a reciprocal of x plus 2. That's your reciprocal function, your basic reciprocal function shifted 2 units to the left. And this acts a whole lot like that. Now there's a vertical stretch involved. Numbers get really big, but that's kind of the way the y equals x squared function acts with the y-axis. If it's not the y-axis, it's x equals -2 because this is like 1 over x shifted 2 units to the left. And then stretch. Okay. Do they understand that or not? The way it is. Okay. Now here, You got an asymptote at this point. We either come up from the negative values, go through zero here. Go through this zero, okay, so we either do this, or we come down from here and go through this. We can't come up from here and go through this point. Because then, to get back down to this point, we'd have to turn around and come back through the x-axis. We can't come back through the x-axis. We don't have a point where this thing, where y would be zero. Y is only zero at these three values, and we've already graphed them. We can't go through the x-axis at any other point. So we've got to come down from here, and then go through here, and go from here, and then go on up. So it's going to come down like this. I'm thinking probably something like this. And that's what our graph looks like. We follow the logical process, follow the algorithm, write down what you're doing at every step, write down these words or abbreviation. Headings of the different things that you do, write it down in an organized fashion. And if you choose to, especially in problems that you're not sure of, send me a copy. Okay, we're going to graph this function, which is a whole lot like this one, except we don't have that x minus 5 in it. And we're not going to have the x squared behavior at the end. Well, 3 dots because we do almost exactly the same thing we did here. We've already seen that this is equal to 0. If we factor it, or use a quadratic form, that's legitimate. But try to factor because it's all easier. Okay, we get x minus 3 or x minus 2. So we can begin constructing the graph. And I never did label it this point. It's minus 1, not minus 2. It makes that a little clearer. That one. Okay, well. Here we have the minus 3, 0, and the minus 1, 0. Y-intercept. Well, it'll be at y equals 3/2. Because of course, all the x terms become 0 if x equals 0. Then we just end up with 3/2. So here's the point. 0, 3/2. We have a vertical asymptote. I'll write this out in some detail. Since I did it before. Okay, there it is, written out a little bigger than it was there, but it's the same as what we have there. So this is a line x equals 2, -2. And then we have the horizontal asymptote. Out. Putting it back to not thinking. We'll look at long run. In the long run behavior, just y equals x. It's like y equals x. Okay, now it's not actually going to be your horizontal asymptote, but y equals x. Let me just say this case. Slant asymptote. And now we want to do a long division. We divide x plus 2 into x squared plus 4x plus 3. And I'm not going to talk us through there. My underline here is in my way. I'll let myself put them all around. So if we find that out, we get x plus 2 minus 3 over x plus 2. Now, as x gets big, 3 over x plus 2 approaches 0 because your denominator gets big. A big denominator into 3 gives us a small result. If the denominator gets really big, we're approaching this term will have value approaching 0. And so x goes to infinity. This, which equals this, approaches x plus 2. So we draw the line y equals x plus 2. So let's see, if this is 3/2, here's 2. And here is the line y equals x plus 2. And now what? Well, y equals x plus 2 is negative down here. And for large x, the value of this function has to be close to this line. Well, the graph has to be close to this line. So the graph is going to come down from here, sort of. And then it's going to slope up here. It's going to approach this vertical asymptote. So there's going to be an asymptote to this slanted line and an asymptote to this vertical asymptote. Asymptotic to this vertical asymptote. Okay. Then on the other side, uh-oh. Yeah, this one. Yeah, okay. My labeling and everything had to go off there for a minute. This is labeled at a unfortunate point, but it's going to go right through it. We come down from this asymptote up through this point. And we got to go through this point, and then we come up here. Now, actually, I think this point is far enough over that we don't really go through this slanted line. So my graph is a little bit off. So it doesn't really quite look like that, but if you drew it like this, I would probably accept it. As I've said before, there are wiggles in this graph, or potentially kind of wiggles, where we change concavity, go from concave down to concave up. And that's something you learn to deal with in the calculus course. We don't learn to do it in this course because you got to have at least half a semester of a decent calculus course before you can begin to do that. Then, if you've done well in the calculus up to that point, it's not difficult. But at this point, it's just totally beyond anything we can think about. Okay, so that illustrates a slant asymptote. And really, I'll show you this graph if you were actually to graph it. This asymptote crosses the x-axis far enough to the left of this point. This is 0. That really the graph looks like this. Comes up here. It goes off. Probably something like that. Not too much different than what I've heard. And that's not quite right. Again, for the purposes of this course, that's just fine. I don't even have to do a calculation to prove that 3/4 minus 1/8 isn't 3 minus 1 over 4 minus 8. Because 3 minus 1 is positive, 4 minus 8 is negative, so this is negative, right? But what's bigger, 3/4 or 1/8? Okay. For this reduction to absurdity. Something is positive can't equal something that's negative. It's absurd to think that it would. Now, it's not absurd to think that this might be the rule because it looks a lot like the rule for multiplying fractions, but that's not the rule for adding fractions. Add fractions, you got to get a common denominator. And subtracting fractions is just adding fractions, but you got a negative. Okay? So please don't ever do that. Okay. So what do we do? The first thing we do when we see this, we say Yeah, denominators. We don't want denominators. They're pain. And if you've got an equation, now if you got a fraction, if you're just trying to simplify this left-hand side, then you're going to have to get a common denominator. But we're not trying to simplify the left-hand side. We're trying to solve the equation, and we can multiply both sides by a common denominator, which is the thing that I've been urging you to do since the first day. Okay. Multiply and return by the common denominator. I'll do this over one because we need to do that, but remember how things line up. And I've said more about this previously. Affect the whole video. So now I've multiplied every term by x minus 4. The x plus 2 and the 1 could switch positions because of the way fractions multiply. See, the x plus 2 goes away. You end up with x minus 4 times x squared plus 4x plus 3 minus. Similar thing happens to the x minus 4 here. You can switch over here and all that stuff, and you get x plus 2 times x plus 3, and that equals 0. Because I have enough mercy to make the right-hand side 0, so we don't have to expand this. Okay, well now we use the distributive law. To multiply x by x squared plus 4x plus 3. This should be familiar. But maybe it isn't, so make sure it becomes that way. And there we have that. And then we multiply through here, we get x cubed plus 4x squared plus 3x minus 4x squared plus 16x minus 16x minus 12 minus x squared minus 3x minus 2x minus 6 equals 0. And I wrote that down kind of clean. I could have done something wrong. We've only got one x cubed term here, so we got x cubed. And then we have an x squared here and an x squared here and an x squared here. Got 4 of them here, minus 4 of them here. We're almost rid of them, but there's that minus x squared. So we have minus x squared. And then we have 3x and minus 3x, which is 0, but we still have minus 16x and minus 2x. That gives us minus 18x. And then minus 12 and minus 6 is minus 18 equals 0. Now, I didn't plan it out this way, but conveniently, we can do some factoring here. But it's not going to help us some of them. We can factor by grouping. We can factor x squared out of this and get an x minus 1. Yeah, factor the 18 out of this, we get like an x plus 1, so it almost factors by grouping, but it doesn't. So now we're kind of stuck trying to find values of x that make this 0, and then dividing and doing all that stuff, and that's kind of a pain. It kind of almost works, but I don't think it's going to. And whenever you have a problem like this that arises like in the real world instead of a math course, you never expect it to accuracy, you don't even bother. Unless you've been instructed to do so. Okay. Now, I noticed that my reduction to absurdity argument is over here once more. This isn't this. You don't subtract the numerators and subtract the denominators. We can reduce this to absurdity. 1/8 is less than 3/4, so this ain't negative. Numerator's positive, denominator's negative, so this is negative. And positive can't be a negative, so it's absurd to think that that works. Okay, that doesn't mean you're absurd if you thought that that works. So don't take it personally, but you have to see that this simply doesn't work. And reduction to absurdity is a standard mathematical argument. Okay, so a reduction to absurdity doesn't say you're absurd if you believe this. It says this does become absurd, be conscious of it, and don't do it. We subtract or add fractions by finding common denominators. Here, we got denominators. We're trying to actually simplify this. We'd have to find a common denominator, which isn't that difficult. And it gets a lot more complicated. It's an equation, so we can multiply both sides by the denominator and they go away. And then we end up with something that's at least reasonably manageable. And it looks a lot simpler than what we started with. Okay.